All right, why don't we go ahead and get started? So welcome everybody to the final, let's say, official lecture of E290C. So nicely enough, I said people should be here, so people seem like they're here. At the end of the lecture today, the Eta Kappa Nu folks will be coming by and you guys will do the course evaluations. So obviously love to get the feedback, see what you guys thought and all that. Obviously we're not quite done. As you guys know very well, there's still the project going on. So next week we'll be doing the project presentations. So obviously that won't be webcast or anything like that. And as we were discussing last time, you should sort of plan for, let's say, nominally about 15 minutes of let's say, if you were uninterrupted presentation, so that, you know, when we interrupt you and it goes about 2x longer than that, we're still sort of reasonably on schedule with everything. Other than that, the actual report is due basically a week and a half from today, so it's Monday, May 9th. So obviously, hopefully you guys have that all in mind. You know, you should be writing up kind of what you think the most relevant and important pieces are. In particular, summarizing kind of the overall design methodology, you know, how far you got, any sort of issues that you ran into. Actually, on that note, so any either questions or anything any trouble people are having with the project? All right, so I guess last time there was like 1.5 group that had the actual adaptation working. How are we doing this time? Still just one group with adaptation, huh? Okay, so where are people at? Well, okay, let's do this. How many people have like a PLL that locks? Okay, CDR locking? Okay, so adaptation is like, oh, there was a halfway hand there or something? So adaptation is just hard, or just people haven't gotten there yet, and, you know, over the next 4 days before your presentation is when everybody's going to be doing stuff. Is that the... Okay, I see. Okay, so unless there's any questions on anything, then we can, I think, go ahead and dive back into things. So last time we were talking about mixed signal verification. And as I said then, that's actually a fairly big and broad topic. I'm not going to claim that I've covered everything that can possibly be done there. But in particular, we spent a lot of time talking about basically doing behavioral modeling in hardware description languages, with the main motivation for that being that you've got this big complex system. You really want to make sure the darn thing actually works, at least from a, you know, really avoiding really stupid mistake standpoint. And in order to do that, of course, it takes a long time to do any sort of reasonable simulation with any kind of detailed model. And in fact, if you really do things in a hardware description language, you can leverage the fact that it's all event-driven to get much, much faster simulation times and much, much faster answers about, okay, yeah, does this thing actually work or not? So we spent, you know, a reasonable amount of time talking about that. I think pretty much the last topic that we sort of got into was just dealing with some of the issues related to the fact that, you know, let's say real wires, or at least even in Spice or Cadence or whatever it is, every sort of node actually carries two pieces of information. It actually carries a voltage and a current. But when you try and model things with these hardware description languages, unfortunately, it can only represent sort of one thing on any one node, right? Either it's a voltage or a current, but not both, okay? Apparently, there are actually some new capabilities that are trying to solve these problems. I haven't personally used them yet, so I won't claim that they work. So instead, generally speaking, people will write all kinds of post-processing or basically deal with the netlist ahead of time to try and ensure that they get that to work. So the particular issue you tend to run into is that, you know, for example, if you want to do current summation, you could say, okay, well, basically you'd have these two subunits. You can model each one of those individually accurately, but then when you put them together at the higher level, they basically would have sort of the equivalent of a drive fight, right? You'd have one quote-unquote voltage source driving the I-out node through that first unit. You'd have another voltage source driving that I-out node through another unit. Okay, so again, basically doesn't work directly. So what you typically will end up doing is, a priori, when you built your schematic in the first place, you'll insert this so-called, you know, special current summation block. So the idea is that that block, when you actually netlist into the real, let's say, Spice or Spectre netlist, it'll just have elements in there that will not change your functionality or your LVS or anything like that at all. Right? So things will still work exactly the way you expect them to. But then when you actually go into the HDL, it'll replace that little, you know, box there with an actual addition. Okay, so that it knows, oh, this was intended to be current A plus current B. Okay? So again, this is a little bit annoying because, you know, you have to sort of do this ahead of time in the schematic, and if you have a really big current summing node, you have to put a bunch of these things. But nonetheless, it works reasonably well. Okay? So beyond that, maybe the other sort of, let's say, high-level message is that when you really are putting together your schematics in the first place, you should think about how that's going to translate into the behavioral model. Because sometimes if you just sort of draw the hierarchy in the right way, it will map much better into the behavioral model. So as an example, if you always draw the boundaries at voltage signals and you always assume everything is a voltage, then you sort of can avoid that problem in most instances. Okay? Does this make sense to people, or mostly just a reminder? Yeah?
How do you make sure that your sort of behavioral models actually match your...
Okay, that's a great question. And in fact, that's something that I'll be reminding people about, or that's something I was planning to say a little bit later on. There are some, let's say, techniques that you could imagine to try and do that. But at least at the moment, I don't know of a formal way that actually says your behavioral model really does match the actual circuit schematic. Okay? Now, again, I think there are ideas as to how you could do that. But indeed, that is, let's say, it's not an Achilles heel, but it's a big issue with these kinds of things where, you know, somebody could write the behavioral model and make a mistake in writing that model versus the actual circuit.
Well,
yeah.
I guess the one thing I was wondering about is, I mean, since you're using different tools to simulate the sort of your verification stuff for the analog blocks and your big picture stuff, it seems like it's more difficult than just, say, validating a Verilog A model.
Well, you're right. It is a bit of an issue, although you can deal with that in the sense that, you know, you can always write routines that would grab data from one and compare them against data from the other, right? In fact, there's some semi-automatic things that you can do for particular types of blocks. So VCOs in particular have, you know, a lot of stuff that's been written about them to try and characterize them and automatically shove them into Verilog. But remember, the thing that is really kind of killer with most of these things is usually not that, you know, somebody thought the current source was value X versus value Y. It's usually like this bit either turns the thing on or turns the thing off. And, you know, the Verilog guy thought it was one way and the other person thought it was the other way. That's usually the things that kind of kill you with these, right? So the real trick there is actually what we sort of touched upon a little bit last time is, to the extent that you can, you really want to write the models as kind of as low of a level as you can. Because the lower the level of each individual model, the less likely you are to make a mistake, right? To make it so that the model doesn't really match what you actually draw in there. But that's something I'll touch upon later, which is that pretty much every time you change anything in your schematic, you better immediately update the behavioral model and immediately rerun all of the tests that you've done just to make sure that you didn't mess something up along the way. It's a great question. More questions? Or? Okay, so let's go ahead and actually move on. So we also showed this example a little bit last time of just saying, so far I had shown sort of simple examples of how you do like current sources and DACs and things like that. Indeed, you can do this for time delays as well. It's a little bit more annoying from a syntactic standpoint, but indeed you can do that. You can actually use it to model things like VCOs, phase interpolators, delay lines, and so on and so forth. And indeed, you will really want to do that to be able to see that your PLL actually does lock, and that it then drives the phase interpolators, and the CDR actually locks, and so on and so forth. Okay? Okay, so the other thing I wanted to just briefly mention, because, you know, it's actually not too complicated, but at first sometimes people don't immediately see how you do it, is, of course, if you're going to be checking things like adaptation and stuff like that, you do want a channel model inside of there, right? So, but of course, you really don't want to be solving like differential equations or anything crazy like that inside of, you know, Verilog or VHDL, because again, the whole point is you're trying to make this thing run fast, okay? So the way you'll typically do the channel modeling inside of the HDL is basically you'll just take some pulse response of your channel. And by the way, you may do this sort of in an oversampled way so that you can actually tell what's going to happen from a timing standpoint. So typically you'll do maybe a 10 to 20x oversampling, right? So let's say just for the sake of, you know, example, let's say that this is what your sort of channel pulse response looked like. Let's say something like that, right? Let's say that, you know, this was 1 t-bit like this. So what you do is you just go, you take each one of those individual samples, right? As an example, at some oversampling rate. Doesn't really matter too much what it is. So you go, you find all of those different samples for however long you need to, right? Much like you guys did, I think, in your equalization methodologies. And then what you do is you basically convert this into an FIR filter. Okay, so in other words, for each one of those taps, you just figure out what that weight actually is, right? And then you just write the whole big expression of, as an example, the output of the channel would just be equal to, for example, you know, the value of the 0 tap times data 0 plus the value of the 1 tap times data 1 plus the value of the 2 times data 2, and so on and so forth. Okay, so basically you just express this whole thing as one big FIR filter. And you just use that to actually run your whole behavioral model against. Okay, now, by the way, typically notice you do need some sort of history in the channel, right? You need multiple data bits, and by the way, these could even be sort of oversampled, right? So what you'll maybe often actually do is internally you'll just write sort of a little shift register that keeps track of all of the data that was sent into the channel earlier, and then use that shift register to actually construct this FIR filter. So you just take the values in the shift register, multiply them by the channel taps, and then sum them all up at the final output. Does this make sense to people, or? Yeah.
How many taps do you typically do?
Okay, well, so it depends on how many are relevant in the channel response itself, A, and B, how accurate of a model or how accurately you want to be checking your overall link, right? So if you're really worried about like really, really stupid stuff, like, just sign bits, you could probably just use a really dumb channel and just kind of roughly see that it's kind of working okay. But actually, I mean, you can get a pretty reasonable amount of information out of these things to check even some of the more subtle kinds of effects. So, and it depends how long the channel response is, obviously, but actually you can get a pretty reasonable degree of accuracy and without actually too bad of a runtime, especially if you're maybe only checking like one individual link. Right? You can imagine if I have a big like switch chip with hundreds of these links, I probably don't want to do a super detailed model for each individual channel. But especially if I'm just trying to verify one link by itself, not too bad to actually take the channel you have, put it into this form, and then use that for the overall simulation. So by the way, just one thing to note here, when you really do this, you have to be careful that you've included all of the parasitics and things like that when you actually got this channel response in the first place, right? Because I'm not solving any differential equations, I'm not doing any real math here, I'm just assuming that the whole thing looks like one big linear system. So when you got this response, it better include, transmitter parasitics and the receive loading and all of that other kinds of stuff like that. Make sense to people, or? Okay, great. So that's actually most of what I wanted to say sort of in terms of the behavioral modeling. A lot of it actually you sort of learn by kind of, let's say, trying to do it and getting some experience. But there are, let's say, some take-home lessons that I did want to point out that I think are sort of important to really learn from all of this. Okay, so the first thing, which is actually something that we mentioned last time, but I'll just write it out on a list so you've got it somewhere. So next time you do a design, you can go back and look at this list. First thing is always write the behavioral model first. Okay? Okay, now the reason I say that is that it turns out that oftentimes, you build your circuit, you start putting all these things together, right? But then after the fact you realize, oh crap, like I partitioned this in a really annoying way, and so if I wrote it this way, like I'm gonna have to go and hack my schematic a whole bunch of weird ways to get it to now fit into my behavioral model in a reasonable fashion. Okay, so indeed that's actually why in all of the project phases I always told you first thing you should do is write a behavioral model. Okay? But actually not only should you be writing like Verilog A behavioral, but actually you should be right away starting out with like HDL behavioral. Okay? Because it's much easier to start with that and then start building around it versus going back the other way around. Okay? Does that make sense to people, or? Okay, so rule, let's say number 2, which is also, touching upon what we just said, is you have to make sure that you update that model with the schematic. Okay, so in other words, every time you change the schematic, every time you add a little control bit, you change, it's current biased versus voltage biased, you add a little resistor somewhere, whatever it is that you do, make sure you're constantly updating the model along with the schematic. Okay, because again, one of the really classic errors is that, at the last minute, you identify something that you thought is not, or that you realize is not quite the way it's supposed to be. You add some small fix that you think doesn't change anything, and then somehow that breaks something else. Okay? So again, these two really have to be sort of in lockstep with each other. And in fact, if you look at some of the more modern, let's say, regression kinds of methodologies, what they really do is that every time you make a change onto something, they'll go back and rerun a whole long set of tests to see if what you just changed basically has any effect on A, the rest of the system, and B, to try and maybe indirectly give you some information about, well, okay, does your model no longer match with your actual circuit anymore? Okay? So again, quite critical that you keep these things actually updated, because if not, very, very easy way to run into trouble. Okay? All right, so The last point should perhaps be somewhat obvious, but I will mention it nonetheless, which is that communicating with your team is critical. Okay, and by team I mean everybody who is putting something onto that chip, or is writing some software for it, or whatever it is. Okay? Because if you guys remember a lot of the stories that I told you last time, a lot of those are just related to, person X assumed one thing and person Y assumed something else. And okay, if they at least talked to each other, that would have already helped quite a bit to ensure that problems didn't happen. Now, having said that, even though I always basically say just talk to each other and most likely the problems will go away. Nonetheless, don't trust that just because you did talk to them, it will work. Okay? So in other words, you shouldn't believe it works until you check it. Okay, so this is kind of another way of saying don't tape something out that you haven't actually verified in any way, shape, or form. And in particular, don't tape something out that you haven't simulated at least once to check that, the wires are connected correctly and, you didn't invert something and there isn't something, I don't know, going off to some place that it's not supposed to be. The power is actually there. Just always double check that, even though you've talked to your buddies, you've talked to the people you're working with, you've checked, just make sure it really is what you think it is, okay? Because, again, it's really, really easy to tape something out that just, doesn't actually really do what you thought it does for very, very silly reasons, okay? And again, this is one of those things where, you spend like 6 months, a year on the chip, it comes back, it doesn't work, your advisor yells at you, just no fun, right? Okay. So, just maybe sort of a final warning that I wanted to give, which is actually, Igor actually touched upon, so I'm glad that we got that out of the way, is that really your verification that you're doing is only as good as your models, right? And of course also your test benches. Okay, so the first issue that indeed touches upon is, there's no formal way for you to check if your model really is the same as the hardware, right? So in other words, you really want to keep those models kind of as simple as you can, or at least, as compatible as you can, because the more compatible they are with the real thing that you're taping out, the more likely it is that they really will match each other, right? Because again, very easy for you to just, I don't know, maybe adding a pin, pin compatibility is pretty easy to check, but you could add some pin onto the analog thing and then just ignore that pin in the digital side, you just add it into the list, but it doesn't do anything. Presumably if it's there in the analog, it was there for a reason, right? So in fact, even things as simple as is this thing powered up or powered down? Put it into the behavioral model. Okay, because believe me, if it's not there, really, really easy to just, have that pin there that then later somebody ties to ground when actually it was supposed to be VDD, right? Just as a very simple example. Okay, so again, make sure you pay very close attention that your model really does reflect, at least grossly, what it is that your schematic is doing. Okay? So kind of what I'm getting at here is that from, let's say, that's definitely critical from a gross functionality standpoint. But actually, in many cases, it's not too difficult to model the real, let's say, behavior, right? Or when I say behavior, I mean sort of more detailed analog characteristics. And the reason I say that is because, sometimes actually things can be caught even with a very, very simple model, right? So just putting in a little bit of delay somewhere, or the fact that there's actually a finite bandwidth, all those other kinds of things can actually tell you pretty quickly, or at least in many cases will sort of catch subtle behaviors that you may not have thought about until you really looked at the entire system. Okay? So a lot of times it is actually reasonably worthwhile to kind of think about what is kind of a fairly simple subset of things you can include that may actually give you some idea later on about, issues that could crop up. Okay? Does that make sense? Okay, so then the other thing which is, very much related to this is you should always keep track of which tests you ran. And of course, not only that, but why you ran them. Okay? And again, basically, every time you change something, rerun those tests. Okay, because usually those tests are associated with something like, okay, I want to make sure that this really bad condition didn't happen. So if you want to make sure that bad condition doesn't happen, but you've changed something, better go back and rerun that test to ensure that that's still the case. Okay? So again, this is now, let's say, this is more my advice or more my experience rather than, let's say, something written in a rule book somewhere. But I think if you follow these rules, you have a much, much better chance of getting things back that really will work. So, any other questions on verification? Or? Yeah?
What kind of tools are available to sort of automate test suites and stuff? I know in software testing there's a lot of stuff that people do.
Yeah, absolutely. So as I mentioned, I think there is a relatively recent movement of people trying to make that kind of thing available for the sort of analog mixed signal verification side of things as well. Although, to be honest, in many ways, you don't actually need anything all that sophisticated. Right? Like if you just had something that was kind of like a database of here's all the sort of tests associated with this particular circuit, right? And then you just go every time you like check and save the schematic, either you hit a button or it automatically launches some Perl script that launches all of those tests. That would already go a pretty long way, right? Now again, as I said, there's some more sophisticated things you can do. And again, there's actually some efforts to make more interesting systems. So let's say one of the ideas is to do what's called sort of active comments. So somehow you embed into the schematic something saying, okay, anytime you use this thing, it should always be constrained so that, this VDS is greater than X or, whatever, the gain is greater than Y, something like that. Embedding that within the schematic is another kind of nice way of doing that. For better or for worse, that's not necessarily in the standard flows. So then, you can go and sort of hack things yourself. But, kind of the most important thing is that it doesn't really matter, I think, too much exactly how you do it. As long as you have some strategy and methodology in place that not only you yourself will follow, but the entire team, right? Because again, it's most of these are much, much bigger than just one designer. Okay, so getting something standardized a priori is obviously pretty critical. Okay, other questions on verification? Okay, great. So if not, let's actually go ahead and move on to the next set of slides. And actually, I guess this will be the sort of final set of slides, at least for this semester. So there's lots of, let's say, more advanced kinds of things that we could talk about. For today, I think I decided to focus on multi-level signaling, and I'll explain a little bit more what I mean by that in one second. But, there's lots of other actually more interesting things going on in links these days. So people talking about doing what's called simultaneous bidirectional, where you actually sort of, transmit and receive at the same time. And that's for actually reasons similar to what we'll talk about with multi-level signaling. Things where people are trying to do, let's say, more advanced kind of coding and decoding types of schemes. So as an example, doing some error correction code to try and hopefully relax some of the constraints on the link itself. But I thought the sort of most interesting one, just because it's kind of a fairly straightforward extension from things we've talked about, but actually also has some interesting issues that will reinforce some of the ideas we've talked about, is really this multi-level signaling. So what do I mean by that? Well, the basic idea with multi-level signaling is, so far we've always talked about so-called binary or 2PAM types of data, right? So we've always said every single thing that I send you just represents either a 1 or a 0. Okay, so like for every single data piece, time slot, I'm just sending you 1 bit, right? But actually, if you think about it, there's no, let's say, fundamental reason why it has to be that way, right? You could actually send multiple bits per time slot, even on one physical wire, but just basically converting that digital information that you're sending into a multitude of analog levels, right? So the next, let's say, simplest example up from the simple, let's say, 1 bit per symbol, which is usually called 2PAM, is something like 4PAM, right? So, by the way, as you can probably tell, PAM just stands for pulse amplitude modulation. The number in front is just the number of analog levels, okay? So 4PAM just means now instead of sending 1 bit every time slot, you're now sending 2 bits every time slot. But in order to represent 2 bits, you need 4 distinct states, right? Which in this case, of course, means you need 4 distinct analog levels, okay? So we'll talk about this some more, but this also leads to some very interesting eye diagrams. In particular, if you sort of look in this region over here, there's all kinds of interesting stuff that happens when you start doing this. But again, we'll get into that into more detail in 1 second, okay? So the first question, of course, is why in the world would somebody do something like this? Why make your life more complicated by sending more than 1 bit per time slot? Okay, why not just like run the thing faster and get more bits, right? Well, okay, so that turns out to be actually a somewhat involved question. But let's actually sort of try and take a stab at this from, let's say, the zero order standpoint first. Okay? So first of all, let's always assume that we have the same peak swing in the transmitter. Okay, so in other words, we're not going to cheat. We're not going to make it so that, if you send 2 bits per symbol, you're actually sending, twice or 4 times as much voltage. But instead, we're always going to keep that peak swing fixed. Okay? So if I'm doing my standard, 2-level kind of signaling, then okay, I basically, at least in the differential systems we were talking about, we're always going to send either +1 or -1. Okay? Okay, so now, if I'm going to do 4PAM, what are the analog levels that I should be using? And by the way, you have some, in principle, you have some freedom here, but obviously there's something that will be better for reasons that we'll touch on in a second. Okay, so what should at least 2 out of the 4 levels be? Yeah, there we go. +1 and -1. Okay, that's easy. Okay, now how about the other 2 levels? What do you want those to be? Where should you put them?
0.5 -0.5.
Ah, okay, not quite. Okay, so, but that's not a bad guess. So you said 0.5 and -0.5. Okay? So now, somebody want to tell me why that's not actually necessarily the best choice?
You have less margin for the top and bottom.
Yeah, there we go. Because notice the distance here is 0.5, right? Distance there, of course, is also 0.5. What's the distance here? 1, right? So what does that mean is going to dominate your bit errors? Those up and that bottom, right? That's where you're going to get the most errors. So what is it you actually want to do?
0.33.
Say that again?
±1/3.
Yeah, there we go. It turns out to be ±1/3. Okay? And the reason for that is fairly straightforward, right? So if I put it at 1/3 and -1/3, then now the distance between each one of those points is equal, right? So basically, since I know I'm going to be dominated by whatever that worst case margin is, I'll just make all of those margins equal, right? So in other words, you're always trying to sort of split the space as equally as you can. Okay? Now, just to make sure it's clear, what do you do with 8PAM? And I'll just go ahead and draw the 2 that should be obvious. And we won't have to fill in all of them just because I'm lazy, but conceptually, what do you do with 8PAM? Like, what's the first level down from +1?
6, 7.
Ah, okay, close. Because remember, I'm doing +-1 and not 1 to 0.
Yeah.
So what is it then? You were really close.
5/7.
5/7, exactly. Okay? So the next level down is 5/7, and then I'll just, I'll write it out. Then 3/7, 1/7, -1/7, -3/7, -5/7. Okay, and again, obviously, I just wrote the numbers down. They're in a linear progression along that vertical line there. Okay? And of course, you can keep on doing this for more and more, more and more number of levels. Okay? Okay, so first of all, what happened to my voltage margin? Did it get better or did it get worse? Yeah, it got worse, right? And in particular, if I said that I told you I'm going to do n bits per symbol, how much did it get worse by?
To the n.
Okay, almost.
-1.
There we go, 2 to the n -1, right? It got worse by 2 to the n bits -1. Okay, so as an example for 4PAM, you'd say, oh, crap, I have 3x worse margin. Now, is that a totally fair comparison, or am I being a little bit mean from a, let's say, signal-to-noise ratio standpoint?
Depends on your channel.
Say that again?
Depends on your channel.
Ah, okay, we'll get into that in 1 second. Let's assume I even have a perfect channel. Am I being fair, or am I being a little bit mean when I say that it's 3x worse for 4PAM?
Bitrate is more, right?
Say that again?
Simple rate is more, right? Bitrate is more, right?
Yeah, my bit rate is higher, right? I have twice as many bits per second with 4PAM as I do with 2PAM. Okay, so how does that help me? Or, what is it that I should sort of rescale if I want to be apples to apples?
By n bits.
Slow down your amplifiers and have less noise.
There we go. It's noise, right? Because basically, if I have the same, to get the same bit rate, I need half the bandwidth, right? So in other words, my sort of noise would be proportional to what? Assuming I, of course, do everything right, you know, I either add the capacitance or I do whatever I need to do to knock the noise down appropriately with the bandwidth. So how would my noise scale? And let's just assume there's some nominal, nominal noise. So what is it? How does it scale with the number of bits?
Just linearly?
Yeah, it scales linearly, right? This would be just divided by n bits, okay? So in other words, if I had some nominal, and let's not call this SNR, let's call this sort of like a relative margin. Okay, and what I mean by relative margin is something like, the transmit voltage over the noise. Okay? So in other words, my relative margin is basically scaling with the number of bits divided by 2 to the n bits minus 1. Okay? And it scales with the number of bits just because, you do 1 over this, and this is obviously decreasing the margin. Okay?
Now it's scaled by square root of
Say that again?
it's now sigma square scale.
Oh, I'm sorry, you're right. Yes, that's actually correct. So this is actually scaled by that. There we go. Okay, so, well, nicely enough, 2PAM, obviously that just sort of, nothing happened, right? That's just sort of as the same margin as it was before, right? How about 4PAM? What do you get? And I don't need a number like, when you compute that out, what does that turn out to be? What does that turn out to be?
0.25.
What is that?
0.25.
0.25. How'd you get 0.25?
5. 2 over 8.
Okay, well, so what is n bits in this one?
Oh, sorry. It's quite
Yeah, n bits is 2, right? So on the numerator, there's like a square root of 2. So maybe you guys are really good and you did like square root of 2 over 3 in your head, and that comes out to be 0.5, but I don't know. I didn't quite get that, I guess. Right? So it's just square root of 2 on the top divided by 3 on the bottom. Right? Because you have 3x smaller voltage, but you have square root of 2 less noise.
About 0.47.
Okay, well, so you're much better than me, or your calculator is. Okay, how about like 8PAM? What's that going to be?
It's about 3.
And by the way, maybe give me the pre-calculator answer first, because I can't do the calculated one in my head.
Square root of 3 over 7.
Yeah, there we go. Square root of 3 over 7. Okay, so what does that turn out to be?
0.247.
Okay, so obviously, this is scaling kind of exponentially, right? It went from 1 to maybe about a half to maybe about a quarter and so on and so forth, right? Which kind of intuitively makes sense because, hey, you're adding more bits, and so that kind of makes sense that it should all sort of go with the number of bits, right? Okay, but so obviously there's some reasons why you'd want to do this, but just based on this, you'd say, well, what the hell? Why would you ever do this? Like, I've just made my SNR worse for the same bit rate, right? It's like immediately seems like this is not a good thing to do. Well, okay, so then why is it that you do this? And okay, maybe not in high-speed links, but in general, why is it that you may want to do this?
Because your channel's really crappy.
Yeah, exactly. So if your channel is really crappy, or just, somebody says, I will throw you in jail if you use more than X bandwidth, then the only way you get more bits is to pack more bits per second, right? Or rather, more bits per second per hertz, to be more precise. Okay? But in really in our context, it really is related to the channel. Okay, now, I'm going to put this in quotes because we're going to sort of maybe throw another monkey wrench into this in 1 second. But it is indeed sort of related to the channel. Okay, so, and the way it's related to the channel is something like the following. So imagine that I sort of plot my channel magnitude response versus frequency. Okay, so let's say my channel looks something like that. Okay, so that as an example, let's say that I'm going to compare two options, right? Option number one is I just do my straight, normal 2 PAM kind of signaling. Okay. And option number 2 is I basically do 4 PAM, but then I use half of the bandwidth. Okay. So just as an example, let's say that this point right here was, I don't know, like minus 6 dB. Okay. But that point right there, maybe I have a really, really crappy, roll off, so that this is like minus 30 dB. Okay, just to make up a number. So, what do you guys think? To zero order, does that look like something where multi-level might be useful? Yeah, maybe, right? Because there's a huge jump in the loss, right? There's like a 24 dB hit you take just from going from that minus 6 dB, just from going from 2 PAM to 4 PAM, right? Okay, so it turns out the classic rule of thumb says something like if it's greater than about 10 dB per octave, meaning greater than 10 dB sort of increase in the loss for every factor of 2 in essentially the channel bandwidth or the signaling frequency, then it sort of says, okay, maybe multi-level signaling is actually better. Okay, that's kind of like the classic rule of thumb. Now, turns out you have to be a little bit careful with that. So why is it that that's not exactly sort of a perfect predictor of whether or not really doing multi-level is beneficial, even from a, let's say, signal to quote-unquote noise standpoint? What's wrong with that?
The ISI.
Yeah, basically, right? So I guess the real point there is that there's a lot of ways you can get from point A to point B that would cause very different ISI profiles, but may have the same loss at those 2 different frequencies, right? So as an example, it could be that, this is totally flat and then has a deep notch right there. Or it could be that, I don't know, some really funky, weird thing happens and, okay, I don't know what the hell the response of that thing would be. But the point is you really actually want to be looking at not kind of this rule of thumb, but at the very minimum you should really look at sort of at least the residual ISI distribution versus kind of how much cursor magnitude you actually get, right? Now, even this is not entirely complete either, because remember, there's also things like, jitter and supply noise and all these other noise sources that we've talked about that will also really come into the picture. Okay, and in particular, as you start doing these multi-level kinds of things, basically you start dealing with really small signals pretty quickly. Okay? And when you deal with those small signals, every small little possible error you could be making is really important. Okay? So like even that, 1, 2 millivolt residual offset in your sampler, if you're starting to deal with only a few millivolts of signal to begin with, really important, right? Okay, so there's one other thing that I should sort of mention here, which is, okay, we've been talking about this as if it's all about the channel. But is that really the only thing that matters in terms of setting the, let's say, the overall power of your link? So one person shaking their head. What else matters? In fact, what else is pretty important?
CDR.
Okay, yeah, there is a CDR, but what's that, what about the CDR? Like, how does that, why is that important, and what would be sort of the trade-off, or the, let's say, the zero-order trade-off between doing 4 PAM and 2 PAM in terms of the CDR? And by the way, you're right, there is actually something pretty direct there.
Well, the jitter magnitude gets sort of proportionally a lot bigger if you're at a higher speed.
Okay, well, so let me rephrase what I think you're saying. You're saying, if from whatever reason I can only build some clock source with X picoseconds of jitter, and that X is just, I just can't make it any smaller than that for either practical or fundamental reasons, right? Well, if I take something that has X picoseconds of jitter and then I run it twice as fast as I used to be running it, yeah, that jitter is more important, right? That jitter is going to be really hard to deal with, okay? So indeed, that may force you to sort of say, well, okay, sorry, I just can't deal with it. I have to sort of do a more precise thing in the voltage domain, right? That's certainly true. But yeah, okay, well, maybe it is hard, but you can actually do a pretty good job scaling jitter down. So what else? And really from a power efficiency standpoint now, let's think about why is it that you might get pushed one direction or the other? What else matters?
Distributing the clock.
okay, there is certainly some clock distribution. It's not actually entirely obvious whether 4PAM versus 2PAM will be lower in terms of distributing the clock, because one has more hardware, the other's at, one has more hardware and is at lower frequency, the other's at higher frequency but has less hardware. So that's not immediately obvious, but that does actually touch upon what I'm trying to get to. And maybe I'll give people a little bit of a hint. When you look at just the power consumption of some broadband amplifier, what's that related to? What's that set by? Just, let's say some resistively loaded common source stage driving a fixed load cap. What's that power proportional to?
FT gain bandwidth.
Okay, it's proportional to the gain bandwidth, and let's actually write this, let's say, more properly. So it's A times omega bandwidth times what else?
Capacitance.
Yeah, there we go. Load cap. Are we done? Okay, there's a V star there. Now are we done? Are we really done?
That's the denominator as well.
Okay, there we go. There's the denominator, right? There's this 1 minus A, basically 1 minus A omega bandwidth divided by omega t times some gamma factor, right? So what happens when you try and push on those circuits really hard? Right? So what happens if you're already at, let's say, I don't know, ft over 3, and you try and double your bandwidth? What happens to your power? Does it double, or does it do something much nastier than that? Yeah, it's a lot nastier, right? It goes up like in this super sharp way, right? You guys remember those curves where we were showing things that did like that? Well, okay, so if indeed you're running into a situation where the circuits are actually what's limiting your overall bandwidth, you just can't freaking run those things fast enough, then actually even forgetting about the channel itself, your circuit may be quote-unquote creating the channel, right? Just the amount of power it takes you to hit that certain data rate could very easily drive you to think, well, okay, maybe I should be trying a different approach to actually get this extra throughput out of the thing, okay? Now, that's not to say that, again, this is actually a fairly complex argument that has been debated many, many times, and with different advocates for different reasons claiming what they wanted. But from a technical standpoint, indeed, if you really do find yourself running in a situation where you just can't get the bandwidth you need, then indeed it may actually make sense to go to these higher level types of modulation schemes. Does this make sense to people, or? Yeah.
So how do you compare this versus like having like let's say doing 4PAM versus 2 in like parallel?
Oh, okay. So here's the trick. I think, well, it's not entirely true, but let's say from a purely energy efficiency standpoint, I could argue that doing two 2PAM links in parallel would always be better. Now, to let's say put a little bit of an information theory hat on, like, that's not really a fair comparison, because to do two 2PAM links versus one 4PAM link, I'm probably using twice as much real estate, right? So like from a resource standpoint, I've like taken extra resources to reduce this other metric I care about, right? I'm obviously waving my hands a little bit because, that's not always exactly the case. But generally speaking, you should remember the reason people like to do serial links is because there's only so many pins you can actually get onto a chip. Not only that, there's only so many pins you can actually escape out of the package. And then by the time you're done with that, there's only so many, wire traces you actually want on the PCB, right? So in general, like especially if you're talking about, very high throughput kinds of systems, there's already as many wires as you can physically pack there into that thing already. Okay, so in other words, the trade-off is usually not about adding more wires versus, getting each wire to be faster. It's you've already put as many wires as you possibly could. Now you have to go faster. Does that make sense? Or other questions on this? Or okay, so this is the kind of, let's say, high-level motivation for why you might actually want to do something like this. But as we'll see, it's not actually so straightforward to really implement this in practice. And in particular, that's not to say that it can't be done, but really doing it in a sort of energy-efficient way turns out to be pretty tricky. Okay, so to sort of see why that is, I just want to sort of walk through kind of from a pretty high level, what would kind of the circuitry look like to actually build even just a 4PAM transmitter and receiver? Okay? So, in fact, what I'm actually going to do is, let's see if you guys can do it. So, I'm going to tell you on the transmitter, I have a, bit 1 and a bit 0 that I want to send. And then at the receiver, of course, I want to be receiving that bit 1 and bit 0 for every, like, you know, clock cycle. So what is my transmitter going to look like? What's like the straightforward thing that I could do? And remember, I'm going to have to somehow translate, you know, those 2 digital bits into the 4 analog levels. What is a block that takes, you know, digital bits in and creates analog levels out? What is that called?
DAC.
Yeah, it's called the DAC. Okay, so in this particular case, how do you think you would build this DAC? And let's just do, you know, let's make life easy. Let's assume that you're okay with doing, you know, a current mode driver.
The current source.
Okay, is it just one current source, or, you know? Okay, so let's do the easy thing. Let's assume we do basically, conceptually, at least 2 current sources, where we shunt the outputs together. Okay, and one of them presumably is twice as large as the other one. And as an example, let's say I take D1 and I take D0 there. Okay? So I'm going to call D1 my MSB and D0 my LSB, and I'm just going to use that to create, you know, analog levels at the output. Okay? So obviously this is kind of, you know, not great because I've now switched to a current mode where maybe the voltage mode was more efficient, but, you know, fine, maybe there's things we could do to maybe make the voltage mode work too. Okay? So to 0 order, that's indeed maybe sort of a reasonable thing to do. As I'll explain in 1 second, you may actually do something ever so slightly different than this, but let's assume that we did that for now. Okay, so now what's the most basic thing I'm going to need on the receiver to again get this to work? Say that again? Yeah, I need an ADC, but in particular, like, you know, what is that ADC most likely going to look like in this context?
It's a multi-level comparator.
Yeah, how many comparators do I need? Is it 4? 3, there we go. Okay, you need 3 comparators. Okay? And so you need 3 comparators for, and I'll just draw them and then I'll sort of indicate why it's 3. So basically what you have to do is, and I'll just draw this in a different color, basically you have to distinguish between each of those 4 levels, right? But to do that, you really only need 3 comparisons, because from those 3 bits that you get out, or those 3 comparisons, you can tell what each one of those 4 levels would have actually been, okay? And so in case it wasn't sort of clear or obvious, that's at 0, this is +1, this is -1, this is of course, oops, that's of course 1/3, and that's -1/3, so the comparison level is at 2/3 and -2/3. Okay? So as an example, this one will be at +2/3, this will be at -2/3. Okay? Okay, so one thing that I just want to sort of point out, or maybe see if you guys have noticed already here, how easy do you think it is to actually figure out exactly what that thing that I called +2/3 and the other thing that I called -2/3 is?
Oh, the same problem as the adaptive loop unrolling.
Exactly. So you have the exact same problem as what happens when you do loop unroll DFE. Because the problem is there is no real analog voltage that sits at that point, right? So all you can do is find the analog voltage above it, find the analog voltage below it, and then pray. Okay, it's maybe not that bad. Obviously, you build a good DAC and all this other stuff, right? But again, it has this same really annoying problem of not having a real analog voltage for you to lock to. Okay? And it turns out that actually this particular issue was one of the main things that really kind of caused people to have a lot of trouble with actually getting these things to work the right way. Okay? Okay, so there's actually one other sort of somewhat subtle issue that is interesting to take a look at. So what I get out of this thing is 3 digital bits, right? But remember, I only wanted 2. Okay? So anybody happen to know how it is you map from these 3 digital bits into the final 2 you actually wanted?
Thermometer code.
Thermometer to binary.
Yeah, it's a thermometer to binary. So what does that look like? And in particular, let me label sort of what these bits, let me call them like this. Okay? So if I want to go from thermometer to binary, and let's maybe actually write out all of the thermometer codes. Right, so those are the 4 thermometer codes I might get. Okay, and just maybe to be clear, this is T2, that's T1, that's T0. Okay? How do I translate that into my 2 binary bits? So B1 and B0. First of all, just what's the truth table? Let's just do that quickly.
1 1 1 0 0 1 1 1.
Yeah, there we go. Okay, so anybody happen to notice how you sort of build the decoder for this? Like, what's the structure for it?
Or the first two and or the last.
Okay, you might be able to do that, but that's not typically exactly how it's done. That may actually work, but maybe I'll just point out, notice for B1 right here, does it look similar to any of the other bits in the thermometer?
Mm-hmm.
Yeah, it's the same as T1, right? So basically you just take T1, you feed that out, you say that's B1. Okay, now that you know that T1 is that, turns out now notice something else that's interesting. So if I know that I'm up in here, the only bit that can change is T0, right? If I'm down here, the only bit that can change, the only bit that can change up here is T2, and down here it's T0. Okay? And notice that T0 down over here does exactly what B0 does. And T2 over here also does exactly what B0 does. Okay, so the way you would typically build this, at least again conceptually, would be something like this. Okay, so if T1 is a 0, you select T0 for B0, select T2 if it's a 1. Okay? So you could indeed do this, but it turns out there's actually a very good reason why you may not want to do this. So, anybody know why you don't want to do this?
Delay mismatch.
Okay, you're right. The way I drew it, there's some delay mismatch. I can fix that. I'll add some dummy buffer or something like that, but it's a slightly more subtle issue.
You want gray coding on the...
There we go. Why do you want gray coding?
So that you don't make, when you have one error in the comparators, you don't make 2-bit errors.
There we go. That's exactly it, right? So notice with this particular encoding, if you get the MSB wrong, sorry, you're totally screwed, right? You get everything completely wrong. Okay? So in other words, it would substantially worsen your bit error rate. Okay? So typically what you will actually do is not really take D1 and D0 there, but actually before that, you'll feed it into a gray coder so that indeed now you map these levels not to sort of have this big MSB transition, but instead as an example, you'd map it so that there's always only one bit changing from one analog level to the next. So an example, you might map it so that this is 1, 1, this is maybe 1, 0, this is 0, 0, and that's 0, 1. Okay, just as an example. So indeed, you'd actually prefer to gray code it simply so that you don't have these catastrophic error kinds of issues.
How bad are the errors? If you make an error, I only see that you make an error at T1, right? So comparing the gray encoded version with the not encoded version, you're making an error anyway. It's just
that's right, but if I made the error, then now I lose both of my bits, right?
That's just you suffer a loss of 6 dB in the
well, okay, so now you have to be careful, because remember, what if you have a DFE in here? Or there's something else that's decision directed, like your CDR loop.
I'm thinking without gray encoder, you're also making one error on 1 bit.
Yeah, but I'm only making an error on 1 bit, right?
Does it really help just, with it?
Practically speaking, it can make a difference, right? Because remember, especially if I'm then feeding this into some decoder, I have, some 8B, 10B or something, and just, I get completely different results than what I expect, right? So you're right, to zero order, maybe you'd say, oh, well, that's only 1 extra bit, but when you start really looking at the whole system, it may actually be much worse than that, right? Okay. The next thing that actually makes your life even more fun when you start dealing with these multi-level signals is if you actually start sort of thinking about this a little bit carefully, actually recovering the clocks for these 4PAM kinds of signals is fun, okay? So just to maybe give you a little bit of a visual picture as to why that's fun, let's actually sort of, if you guys remember those trellis diagrams we drew, particularly for like the loop unrolled kind of thing, let's do the same thing here, okay? So now let's start thinking about, for each one of those data points, what's the possible transitions it can make, okay? Okay, so if I start on this upper one right here, it could go there, could go here, could go here, right? If I do this bottom one, this middle one right here, that could go here, that could transition to there, or it could transition to here, right? Well, okay, if I do this next one, that could go there, that could go here, or it could go there. And oh, sorry, by the way, this guy could also go there, there, or there. Okay, so if this looks like a mess to you, it's supposed to be a mess. It really is that mess. Okay, because there's all kinds of possible transitions there, right? Because basically any one of those 4 points can go to any one of the other 4 points, right? Or at least the other 3 points, I should say. Okay, so what would happen if you just took this and you just straight fed this into like a normal, clock and data recovery loop? What would that thing do? What would it do? And again, when I say normal, I just mean like, you just have one edge comparator that's always comparing like, the same way we did with 2PAM. What would that loop do? Yeah, it would dither all over the place, right? Because you're feeding this huge multimodal distribution into it, right? So you're going to have horrible performance. So it turns out that with 4PAM and with, in order to recover the clock, basically data filtering is really a must. Okay, because if I actually sort of partition these things out, what we'll see is that, if I really do filter the data, I actually can get reasonably good timing information. It's just that I need to sort of, keep track of, or at least be very careful about which things I look for and sort of what I compare them against. Okay? So, first of all, let's just sort of think about like, what's like the one normal transition that you could have in this thing? Like what's the thing that, if it happens, looks a heck of a lot like what would have happened in 2PAM anyways? What transition is that?
1 to -1.
Yeah, basically if I go from +1 to -1 or vice versa, right? So that one, hey, that's just like 2PAM, right? So in other words, that one, if I set my slicer level just right here at 0, okay, I'm good. I'll sort of get, a nice timing decision there, right? Okay, so the next thing that can actually happen is usually what's called sort of the, let's say, mid-level transitions, which is now, notice in that previous one you sort of did the biggest possible voltage transition you could. These mid are sort of like the next largest transition you can make. Okay, so as an example, that's from here like that, or from here like that. Okay? So now if you wanted to use these, but still get the same time crossing point as you got for the MSB, where should you be placing your slicing levels?
-2/3.
Yeah, exactly. You actually place them at the same point as these datas are. Okay, because that's exactly what they cross through. Okay, so it's +2/3. Oh, sorry, actually, yes, that's right. And -2/3. Okay? And actually, okay, well, actually, sorry, I should be a little bit more careful. My drawing is just not perfect, so let me actually do this a little bit more carefully. Okay, so let me just do this so that it's really right. So these are supposed to be spaced kind of equally from each other. So this is at 1/3, that's at -1/3. You have a transition like that, transition like this. And okay, now that I at least drew it slightly better, this is actually at 2/3 over here, and that's at -2/3 right there. Okay, so basically they cross through the center point like that.
Is that right?
Oh no, sorry. No, actually I did have it right before.
Yeah.
Okay, I'm sorry. There we go. So actually you do put them at 1/3 and -1/3. Okay, so sorry, the confusion there is where you actually put them is where the actual data levels are, and not where your slicers were before. Okay? So by the way, that is actually one piece of at least good news, which is maybe the first good news we've had. That one, there is a real analog level you can find, right? So there is something there that you can find to set that thing to. Okay? So the last ones that you can find, or the last types of transition, are these so-called minor transitions. So these are all the ones with kind of like the lowest possible voltage swing you can get. Okay, so all of those are basically like kind of going between the adjacent voltage levels. Okay, like this. Okay, so now for these, where do you want to set your slicing points? Well, first of all, how many slicing points should you have if you, again, you want to get the sort of same timing information? Yeah, 3, right? So 1 right there, 1 right there, and 1 right there. Okay, so nicely enough, this one's at 0. That one we had anyways. So that one we're good with. Okay? This one is now indeed at 2/3. And this one is now indeed at minus 2/3. Okay? So those other two, well, again, unfortunately, there's no real analog level we can find to set them to. But the good news is that, you know, or maybe the not as bad news is that that's the same place as your data slicers are sitting anyways. Okay? So what this really sort of tells you is that, you know, you can maybe sort of deconvolve something from this mess if you really look for the particular types of transitions and then figure out which actually comparators should you be using to detect the timing for those particular transitions. But you can kind of see, like, if I want to use every single transition, there's a lot of hardware you'd need. Right? You'd need something like 5 comparators if you really wanted to use every single kind of those transitions that's possible. So just like we talked about with sort of the loop unrolling kinds of stuff, basically there's kind of this trade-off between having more samplers and more hardware versus kind of how fast or how many of the transitions do you actually use, right? So in other words, the more hardware you have, the more transitions you're going to get. Now, the only other thing to keep in mind is that not all of those transitions are equal. Okay, and by equal, what I mean by that is sort of their quality is not all kind of the same as each other. So when I say that, what do you guys think is sort of implied by it? What's kind of different between these different transitions? This is again something we talked about, with loop unrolled DFE. What's different about, for example, these transitions versus that transition? Yeah, the slope, right? So notice as you move from the right to the left, the slope of those transitions is getting smaller and smaller, right? So that kind of tells you there's, again, this trade-off of, well, okay, does it make sense to add the extra hardware to grab that information? Or, is the slope kind of small enough that maybe I wouldn't even be getting all that great of an estimate anyways, and I should sort of just throw it away, right? And then save myself the power consumption. Okay, so again, not entirely obvious. Really obviously strongly depends upon what system you're looking at, and, what kind of, let's say, PPM offsets and things you need to be dealing with. But indeed, you can notice that, really use sort of all the information that's there very quickly adds up in terms of the hardware, right? So just right off the bat, if I wanted to grab all of these things, I'd need something like 5 slicers, right? And even if I only use, let's say, these and these, I would need 3 slicers for the edge and another 3 slicers for the data, right? So again, very quickly, a lot more hardware, right? In fact, actually, it's in some senses maybe even a little bit worse than that. Because now let's actually start thinking about what happens when we try and adapt to these things. So if you guys remember in like 2PAM, right, where your eyes look something like this, usually we would say, okay, maybe we'll just put sort of one data level up over here. Right, we'd put one adaptive sampler up at that, at the high level for the data. So how many data levels do you have in this 4PAM thing now? And the answer should be obvious, by the way, from the question. Yeah, you've got 4 levels, right? Okay, so now you could obviously put 4 individual DLEV samplers. You probably don't want to do that because, now we went from, let's say we had, 3 data samplers. We said we could have up to like 5 edge samplers. And now if you put another 4 samplers for the data level, now you're at like, 13 samplers or something like that. So hell, why not just build a freaking ADC and be done, right? Okay, maybe I'm being a little bit mean, but, most likely you're not going to want to do that. Okay, so you probably, again, will only want to use 1, right? Or maybe at most 2. Now, why is it that I say that you're probably only going to, or rather, when I say you're only going to choose 1, what's the sort of penalty for doing that? What are you giving up by only choosing 1? Say that again, Yida?
Oh, I didn't say anything.
Oh, okay.
Convergence time.
Yeah, convergence time, right? Because if I only choose one of them, then roughly speaking, only 1/4 of them, only 1/4 of the time do I actually get a valid update. Okay? Now, by the way, just to make sure it's clear, even though I'm only using one of them, everything should still work, right? Because the whole system is linear, meaning whatever errors I see around there should hopefully be the same as the errors I see around here. But, you know, if your circuits are not exactly linear or something like that, and by the way, just give me a couple minutes. If your circuits are not exactly linear or something, then, you know, then you have to really be careful, right? Because if your circuits aren't perfect, then now what could happen is the errors that are up over here, unfortunately, are not the same as the errors that are there, right? So then your adaptation will not exactly give you the right answer, okay? But again, indeed, sort of it kind of comes down to you have to sort of do this trade-off between how much of the possible information do you use versus how complex is the hardware you have to actually build the darn thing, okay? Okay, so this is kind of, let's say, a whirlwind tour of multi-level signaling. I wouldn't claim that that's everything. Oh, by the way, you know, I mentioned this in terms of adapting the equalizer. Turns out building the feedback for this equalizer is also not necessarily the most fun. Because, you know, everything that used to be a 1-bit DAC is now a multi-bit DAC, right? And so then, by the way, you have to adapt that multi-bit DAC, not just, you know, each individual thing. So that's also fun, to put it in quotes. But to kind of just, you know, briefly summarize a little bit, there's one, I think, you know, very key point that I wanted to make here, which again has been something that, you know, I've been hammering on many, many times here. So kind of intrinsically, when you want to do multi-level signaling, what is it that you're doing to your signaling path? What is it you have to do to make multi-level signaling work on the signaling path in comparison to 2PAM?
You're loading your high-frequency path.
Okay, loading it with what? Or, you know, in what way did we say that was the really bad thing that you don't want to do?
Putting your I mean, it's your configuration in the high-frequency path. It's the
dynamic range, right? So in other words, if I do multi-level signaling, oops, by definition, what I'm doing is I'm increasing the dynamic range on the high-speed signaling path, right? And again, that's just completely by definition now. Now there's no tricks or games you can play, because by definition, you've put more dynamic range into your signal to get more bits, right? So indeed, this tends to be not so great. Okay, you very quickly pay a lot of hardware just to get sort of not as much bits per second back from it. Okay. Now, so by the way, that's kind of generally why it's not used. At least not in, let's say, current backplanes and sort of chip-to-chip links. Okay. And again, it just goes back to the thing that we've said many times, which is, you know, anytime you want dynamic range, keep that out of the signaling path, right? Because as soon as you put dynamic range on the signaling path, you're going to pay for it. Okay. Now, despite that fact, which, you know, unfortunately this is fairly damning, but to maybe recover a little bit for the multi-level signaling story, is that even though that's the case, this could actually be something that you sort of have to resort to, that you just don't have a choice, right? So for example, if you think about things like either Ethernet or even a lot of the wireless stuff, where indeed bandwidth just is very, very heavily constrained, you just don't have a choice. You really have to use multi-level signaling. Okay? And one could actually argue that this may indeed happen in the links domain as well, because if you really keep on pushing on these data rates, you can very quickly get to the point where the channel is just completely destroying you, right? And if that's the case, then indeed maybe it is better off to build something like a multi-level signaling versus actually trying to push really, really hard on all of the equalization and things like that. Or alternatively, if, you know, technology continues to not sort of scale the way it has been, meaning your transistors aren't really getting faster, but you want more and more throughput, then again, you may not just have any choice left. Okay? It's not to say this has happened, but this is kind of the reason I wanted to actually talk about this a little bit, because, you know, you can see scenarios where you may again be forced into really sort of dealing with this again. Okay? The other thing that I'll maybe just briefly mention is that, you know, as you kind of noticed, there's a lot more bookkeeping, right? There's just a lot more stuff you have to get right. You have to get sampler, you know, a bunch of samplers set in the right place without really having, you know, great feedback loops to force them and things like that. So just a lot more sort of stuff you have to keep track of, and then particularly from a, let's say, power consumption standpoint, the more stuff you have to keep track of, the more likely it is you're just going to pay a lot of overhead for that. Okay? Does this kind of make sense to people, or? All right, so any last questions on this? Or actually anything? Okay, great. So if not, we're done with sort of, the core lectures. We're still going to be doing the presentations and stuff next week. But, it's been a pleasure teaching the class, and I hope you guys enjoyed it. So with that, we'll let the Eta Kappa News guys go. So see you guys next week.